When I was first starting out trying to build a synthesizer, I could only really find two types of oscillator designs. Either that simple but not really usable, or with all the bells and whistles you could wish for, but way too complex for a beginner. So once I found my way around this stuff, I was curious to see if I could cobble together a kind of baseline VCO, as simple as possible while still being musically useful. And here's what I came up with. An analog sawtooth core oscillator with reasonably accurate volt per octave tracking, made from just a handful of really cheap components. And because it has that volt per octave tracking, you can use it with most standard sequences, like this SQ1 for example. To understand how it works, let's first talk about what an oscillation is exactly. You're probably quite used to seeing the little waveform symbols on your synth. There's a few different shapes: square, triangle, sine, sawtooth. Some VCOs even have weird ones like shark fin or reverse sawtooth. Now the question is, what are these waves made of? In other words, what is oscillating here? You could, of course, be blunt about it and say electricity, obviously. And you would be kind of right, but unfortunately that answer is not really helpful. We need to be a little more precise here. Before we go on though, I want to warn you, I am not an electrician, so my explanations might be overly simplistic or even a little off. But so far they've worked for me. Just take everything I say here with a grain of salt. With that out of the way, let's talk about electricity. Electricity basically has two main properties that we're able to measure: current and voltage. Since it's hard to visualize those on account of electricity being invisible and all, people settled on using water in a pipe as a metaphor. So imagine you have a pipe filled with water, closed off at both ends. Since no force is applied to the water, it's not moving. Also, we could say that the pressure in the pipe is at a kind of neutral level. This situation is comparable to what's happening inside this piece of wire at the moment. Since there is nothing pushing electricity into it, there is neither a current nor a voltage, with the current being movement while the voltage would be pressure. If I hold one end of the wire to the positive terminal of this battery though, the story changes. Imagine that we connect a water pump to this end of the pipe, while the other end is still closed off. The pump will now start pushing water into the pipe, but since the water can't move out the other end, we're only going to be raising the pressure inside the pipe. And that's roughly what's happening with our wire and the battery. No current is flowing, but the voltage inside the wire has been raised to 9 volts, since it's a 9-volt battery. Now, if I were to turn the water pump off, we can expect to see the pressure inside the pipe return to the initial neutral level. Same deal with our wire. If instead of the 9 volts from the positive terminal, I would apply 0 volts from the negative terminal, the voltage in the wire would equalize. If I'd be able to repeat this process at a high frequency, say 100 times a second, I'd have created a 100 Hz electrical oscillation. And what does the waveform look like? Let's check out a quick diagram. Here the x-axis is showing time, while the y-axis is showing voltage. Now, for simplicity's sake, we're assuming that the switching between 0 and 9 volts is instant, and that the time in either state is going to be exactly equal. If that's the case, we'd get a graph like this for our thought experiment. And, surprise, it looks like a square. This is what a square wave really is, an ideally instant, constant swinging between two fixed voltage levels, where the waveform's height determines the volume, while the width determines the frequency. Same idea applies to all the other waveforms. They're just characteristically shaped repeating voltage swings. With that in mind, let's look at the one we're trying to produce here. So there's two distinct phases in this waveform. First, we have the initial almost instant rise, followed by a constant slower decline in voltage. What's interesting about this, and that's why I've chosen this waveform for my oscillator, is that a sawtooth wave's frequency is solely determined by the duration of its second phase. The longer it takes for that voltage to fall down, the lower the frequency of the wave, and vice versa. This makes it comparably easy to manipulate that frequency. But before we get into that, let's take a look at our basic oscillator core. So at the center of it all, we're using just 4 components: a capacitor, a Schmidt trigger inverter, a diode, and a resistor. That's all that's needed for a fixed frequency sawtooth oscillation. To understand what these components do, let's talk about water again. We'll tackle resistors first. While a conductive wire is like a very big pipe where lots of water can pass through, a resistor is like a narrow pipe that restricts the amount of water that can flow. The narrowness of that pipe is determined by the resistance value, measured in ohms. The higher that value, the tighter the pipe. A capacitor is a bit like a balloon that you can attach to the open end of a pipe. If there's some pressure inside the pipe, the balloon will fill up with water until the pressure equalizes. Then, should the pressure in the pipe drop, the balloon releases the water it stored into the pipe. The maximum size of that balloon is determined by the capacitor's capacitance, which we measure in farad. Diodes are basically like one-way valves. Water can only pass through in one direction. That direction is indicated by the arrow in the diode symbol. So any water trying to move in this direction is blocked. It can only go from here to here. Finally, there's the Schmidt trigger inverter. You can think of that like 2 separate things. Over here, there's a sensor that measures the pressure inside an attached pipe. On the other side, there's a water pump. This pump's operation is controlled by the sensor. Whenever the pressure at this point is below a certain threshold, the pump will be working. If the pressure is above a second threshold, the pump won't be working. Here's a quick graph to visualize that. This line represents the pressure at the sensor, while this line shows the pressure at the pump's output. So every time we cross this threshold on our way up and this one on our way down, the pump changes its state. One thing that's very, very important to keep in mind, no water flows into the sensor. It's really just sensing the pressure without affecting it. So let's put all of this together now. When you're trying to analyze a circuit like this, it's always helpful to imagine a snapshot of a state 0. So in the very beginning, once we put this together and turn it on, what's happening here? Well, we can start out by looking at this point. We'll keep track of the pressure level here by tracing it as a graph. So initially, there will be no pressure here because the capacitor is empty and nothing is passing through our diode yet. So we start out down here. And that means that the sensor here is telling the pump to start working because we are below the lower threshold. So now we have a flow from this point through our diode to this point. Next, there's 2 ways to go for our water. Through this resistor to ground and into the capacitor here. But what exactly does it mean when electricity is going to ground? To stay within our analogy, imagine that ground is basically what's behind an opening in our pipe system. It is a wide open space into which our water can be released. And that means that through this part here, our water can leave the system for good. How much? That depends on the resistor value here, or the narrowness of this pipe, and the pressure at this point. With the capacitor path, it's a little more complicated. If it's completely empty, this is virtually indistinguishable from a straight connection to ground. The balloon is empty and you can dump water into it effortlessly at first. But as it fills up, it starts to push back. It gets harder and harder to push more water in. until the pressure here is not strong enough anymore. And now the capacitor looks like a dead end, as if the pipe's just straight closed at this point. Okay, but what happens with our water coming from over here then? Well, since at first our capacitor is empty, this is the path of least resistance, so pretty much everything will flow into here. But while the capacitor is filling up, the pressure at this point will increase rapidly, because now the only way out is through this resistor, where just a very limited amount of water can leave our system. The lion's share is going to accumulate here, raising the pressure. So on our graph, we'll see a very, very steep rise. But an increase in pressure at this point is at the same time registered by the Schmidt trigger sensor. So as a reaction, the pump will instantly stop working once the capacitor is charged and the pressure passes the sensor's upper threshold. So let's assume we're in this state now. The capacitor is charged enough so that the sensor here tells the pump to shut down. This means that no water is being pushed through our diode anymore, which in turn means that our capacitor has no opposing force anymore. We've essentially stopped pushing water into it, so our balloon will push its contents back into the system. And where does the water go? Well, it can't go this way because the diode is blocking that. There's only one pathway this time, through our resistor and to ground. But because that resistor is restricting the amount of water that can pass through, our capacitor won't discharge instantly. It will take some time. So on our graph, we'll see a slow decline. This will keep going until we reach our Schmidt trigger's lower threshold. Once we pass that on our way down, we'll be basically restarting the cycle, because now the pump will flip on again and everything repeats. The capacitor will be charged, the pump turns off, the capacitor discharges via our resistor, and so on. And that's really all there is to a very basic sawtooth oscillation. But don't take my word for it. Let's build this and see if it actually works like that. Here's everything we need. A breadboard, some sort of power supply. You can use a 9-volt battery, but I am using my self-built dual supply. A 2.2 nanofarad capacitor, a 100k ohm resistor, a small signal diode, and for the Schmidt trigger inverter, I am using a 4106 IC, which is 6 of those in one single chip. And to start off, let's look at how the chip works. Here's a pinout diagram. To get the chip working at all, we need to connect this pin to the power rail, while this pin needs to be tied to ground. Then we can basically choose any of these inverters to be the one we'll be working with. I'm picking the one down here. There's one catch to using this chip though. We need to connect all the unused inputs to ground, because otherwise they might pick up static noise and make the inverter we do use act irrationally. So first, let's set up that chip. Next, I'll put in the diode. Orientation is important here. If you look at it closely, you'll notice this thick black stripe on one side of it. This represents the line in the diode symbol, meaning that current can only flow from here to here. For the capacitor, the orientation doesn't matter, but beware, that's not true for every type. I'm using a foil capacitor here, which is non-polarized. Electrolytic ones, on the other hand, are polarized. Make sure to keep this in mind. Then I'll add in the resistor. Here the orientation also does not matter. Finally, I'll connect my power supply to the breadboard's rails. And now this should already be oscillating. To check on that, I'll use an oscilloscope. An oscilloscope works pretty much like the sensor on our Schmidt trigger. It's detecting pressure levels and then drawing them onto a screen. This makes it a very useful tool for monitoring and troubleshooting. To use it, I'll first have to connect this wire to our circuit's ground. and then connect this wire to wherever we want to monitor the voltage levels. In our case, that would be right here, at the intersection of Schmidt trigger input, capacitor, and drain resistor. And yes, we're actually seeing what we expected to see. First, a near instant rise in pressure, followed by a slower decline. And this waveform just repeats indefinitely. So our basic oscillator seems to be working. But what good is an oscillator that you can't hear? Right, so let's figure out how to connect this to a sound system, or headphones, whatever you prefer. You might be tempted to just attach an audio jack socket right where we plugged our oscilloscope in. Generally, that's going in the right direction, but sadly, it won't work at all. Let me demonstrate. The wave just disappears. And that actually makes a lot of sense, because what we're effectively doing is providing an additional path for our proverbial water to flow into. That way our capacitor is never being charged, because all of the current is leaving through our audio jack. So by trying to listen to the oscillation, we're actively stopping it, because we are tampering with the construction of the whole thing. To avoid doing that, we will need to use a buffer. Buffers also work with pressure sensors, but they use them to simply mirror or copy the voltage levels that they detect. And since no current is flowing into the sensors, they are not interfering with what they're attached to. That's why they are a perfect fit for our problem here. With a buffer, we can leave our oscillator structurally intact and working, while still being able to listen in with our sound system. To build a buffer, I'm going to use an op-amp, set up like this. This way we'll have our sensor on this side, while over here we'll get our copy of the sensed voltage levels. Sounds simple enough, but there is a catch. This is the pinout diagram for a TL074, which is 4 op-amps in one chip. Now with our 4106 we had a power and a ground connector, but with this chip there's power and negative power. What's up with that? Well, the thing about voltages is that they're always just relative. If we talk about a 9-volt battery, for example, all we really know is that the voltage difference between the two terminals is going to be 9 volts, if your battery is fresh. So what we're basically doing there is that we're picking a pressure level to call 0 volts, and then measure everything relative to that pressure level. But that means that 0 volts doesn't necessarily mean no pressure at all. And that's where negative voltages come into play. Because by our definition, any pressure level below the one we picked to be 0 volts must be below 0 volts and therefore negative. So having a positive, a ground, and a negative rail is really just having 3 distinct pressure levels to work with. Okay, but why is that necessary for our buffer? Well, it's mostly to prevent distortion. Op-amp buffers do just fine when they have to copy voltage levels that are comfortably in between their positive and negative supply rails. But if those voltage levels get close to those rails, the buffer can't accurately reproduce them anymore. So while we could just hook it up to our positive and ground rails, we should instead use positive and negative rails, just to provide it with enough headroom and prevent distortion outright. If you have a dual power supply like this one, that's not a problem. But what if you want to use batteries instead? Thankfully, that's totally doable. You just need to connect 2 9-volt batteries like this. If you do that, the negative terminal of this one becomes your minus 9 volts, while the positive terminal of this one is now your plus 9 volts, and the other two combine to become your new ground. Easy. So let's add our negative power rail to the breadboard and set up the op-amp buffer. Okay, so now that our buffer is done, we need to connect it to our oscillator core, right where we've plugged in our oscilloscope. So can we listen to it, finally? We could, but we might get a very distorted signal and/or wreck our speakers doing it. And that's why there's a few more precautions to take. The first one of which being to install a coupling capacitor. To understand why that's necessary, we'll have to talk a bit about offset voltages. Remember how we said that electrical oscillations are just swings between two voltage levels? The thing about that is that those voltage levels could be up here or even down here in the negatives. It doesn't matter. You'd still have the same oscillation and waveform, but its center is shifted either upwards or downwards. Normally with audio signals, that center would be around 0 volts, so right here in the middle. But these two oscillations have what we call an offset voltage. +5 for this one, -5 for this one. And if we look at the graph for our oscillator again, this is also off-center. That is not ideal for audio signals because it might cause an amplifier to distort the sound. So what we need to do is remove any offset voltage from our oscillation. Thankfully, doing that is really easy. We just need two components, a capacitor and a resistor, set up like this. Here's how it works. First, imagine two pipes being connected with a balloon kinda between them like this. Now no water can get from one pipe into the other, since it's blocked by the balloon. But, and that's the kicker, water from here can still push in this direction by bending and stretching the balloon, causing a flow in the other pipe by displacement, and vice versa. Next, we'll have to bring in our resistor after the coupling point, going straight to ground. This acts like a kind of equalizing valve, and that's how we knock out the offset voltage. Because now imagine we apply a steady 5 volts from this side. Then on this side, we'll read 0 volts after a short amount of time. Why? Well, we are pushing water into the balloon with a constant force from here. The balloon is stretching into this pipe, pushing water in this direction. If we didn't have the equalizing valve here, there'd be nowhere to go for that water. But since we do have it, the excess water can drain out through this narrow pipe, out of the system, until the pressure is neutralized and no water is actively flowing anymore. Okay, so now imagine that the pressure on this side starts oscillating, let's say between 4 and 6 volts. When we start to go below 5 volts on this side, the balloon will begin contracting, basically sucking the water in this pipe to the left. This will create a negative pressure level here, like as if you're sucking on a straw, making the voltage drop below 0 volts. Then, once we've completed the bottom half of our waveform, we go above 5 volts on this side, and our balloon will inflate and stretch out again, pushing the water here to the right. And the pressure will go positive, making the voltage rise above 0 volts. So we've recentered our oscillation around the 0 volts line. But what about the resistor? If water can escape through here, doesn't that mess with our oscillation? Well, technically yes, but practically we're choosing a narrow enough pipe here to make the effect on quick pressure changes negligible. Don't take my word for it though. Let's try it out. I'll add in a 1 microfarad capacitor and a 100k ohm resistor after our buffer. And now let's hook our oscilloscope up to this point. Ideally, our sawtooth will look as pointy and sharp as ever. Looks good enough for me. So, can we listen in now? Well, we're almost there. But as a final touch, we should decrease the volume of our oscillation, because a very loud signal like this can, again, damage your amp or your speakers. To do that, we will use a voltage divider, which is just 2 resistors set up like this. Here's the input, and over here is the output. If R1 and R2 are the same size, the output voltage will be half of what the input voltage is. How does it work? Let's use our analogy again. So we have a pipe on this side, where water is being pushed in this direction with a specific amount of force. Attached here is a narrow pipe, which represents R1, followed by another wide pipe. Then down here, there's this other narrow pipe representing R2, where water can exit the pipe system. Finally, imagine we have a pressure sensor attached right here. Okay, so first think about what would happen if R2 was completely closed off. Our sensor here would tell us that the pressure in this pipe is exactly the same as the pressure in this pipe over here, because the pushing force from here has nowhere else to go. It has to accumulate over here. On the other hand, imagine R2 would just be a wide opening. Then the pressure here would be zero, because it would all escape through here. But what happens if R2 is neither completely closed off nor wide open? Well, then the pressure here would accumulate to varying degrees, depending on the narrowness of the two resistor paths. So if pipe R1 is wide and pipe R2 is narrow, most of the pressure will be retained here. But if it's the reverse, the pressure level will be only a tiny fraction. And if R1 and R2 are identical, the pressure here will be exactly half of what we send in here. So since an oscillation is really just a swing between voltage levels, we should be able to scale or divide it down by using this method. To see if that works, let's first check the size of our original oscillation on the oscilloscope. So you can see that the oscillation is between the bottom of this square and the top of this square. So we could say that it has a height of 3 squares. And now I'll set up our voltage divider with two 100k ohm resistors. And I'm expecting to see the size of that oscillation to be cut down by half. Yeah, that looks about right. Now the oscillation is about 1.5 squares high. So now we're finally good to connect this to an amp. And there you have it, even though the frequency is really a bit too high. But dealing with that is going to have to wait till the next episode. Then we will figure out how to change the frequency both manually and using a voltage.